Next topic is heating effect of electric current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. To maintain the current, the source has to keep expending its energy. A part of the source energy is maintaining the current may be consumed into useful work. Rest of the source energy may be expended in heat to raise the temperature of gadget. We often observe that in our daily life, for example, an electric fan becomes warm if used continuously for longer time. On the other hand, if the electric circuit is purely resistive, that is a configuration of resistors only connected to the battery, the source energy continually gets dissipated entirely in the form of heat. And this is known as the heating effect of electric current. So what is the heating effect of electric current? The heating effect of electric current is when the flow of electrons through a conductor causes the atoms in the material to shake or vibrate, producing heat as a result. That's why wires can get warm when there is electricity flowing through them. This is the heating effect of current. यानी जब भी इलेक्ट्रिसिटी ज़्यादा टाइम तक फ्लो होगी किसी भी कंपोनेंट से तो हीट जनरेट होगी. When electric current flows through a wire or any conductor, it's like a stream of tiny fast moving particles called electrons. Now imagine these electrons are like little workers moving along a conveyor belt. As these electrons travel through the wire, they bump into the atoms of the material they are flowing through. Now, when these electrons bump into the atoms, they transfer some of their energy to them. This causes the atom to start vibrating more vigorously. And all these shaking and vibrating of atoms generate heat. It's like rubbing your hands together to warm them up. The more electrons flowing through the wire and the more obstacles they encounter, the hotter the wire gets. So this is the heating effect of current. And this effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the source is P is equal to VQ upon T. It's equal to VI. Or the energy supplied to the circuit by the source in time T is P into T. That is V into I into T. Means it is VIT. What happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H reduced in time T is H is equal to VIT. Applying Ohm's law, we get H is equal to I2 into RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance. Directly proportional to resistance for a given current, directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, then H is equal to I to RT is used after calculating the current through it using the relation I is equal to V upon R. For example, an electric iron consumes energy at a rate of 840 watt when heating is at the maximum rate and 360 watt when the heating is at the minimum. The voltage is 220 volt. What are the current and the resistance in each case? So, the power input is P is equal to VI, thus the current I is equal to P upon V. When heating is at maximum rate, I is equal to 840 watt upon 220 volt is equal to 3.82 ampere, and the resistance of the electric iron is R is equal to V upon I, 220 volt upon 3.82 ampere is equal to 57.60 ohm. Second case is when heating is at the minimum rate, I is equal to 360 watt upon 220 volt, it's equal to 1.64 ampere. And the resistance of the electric iron is R is equal to V upon I, it's equal to 220 volt upon 1.64 ampere, it's equal to 134.15 ohm. Next example is 100 joule of heat is produced each second in a 4 ohm resistance. Find the potential difference across the resistor. H